So up next is Dr. Gerardo Cisneros-Stoianowski, HPC Applications Performance Specialist with the HPC-AI Advisory Council. Dr. Cisneros is a member of the Mexican Academy of Sciences and the American Physical Society, and a life senior member of the IEEE and the IEEE Computer Society. Dr. Cisneros is author or co-author of over 40 papers on applications of computing to solid-state physics and quantum chemistry, and on programming languages for symbolic manipulation. Today, Dr. Cisneros will provide an introduction on NEMO. Dr. Cisneros, you may begin.
Thank you. So I'm going to talk about the NEMO ocean model. That's going to be a part of the competition this time around. And so NEMO, and so why is this not advancing? I'm sorry, I'm having trouble with my laptop advancing the...
You can use the mouse, click the presentation, then you can move the
there you go. Yeah, I just found it. Yeah, sorry. So what is NEMO? The NEMO is an acronym that expands to Nucleus for European Modeling of the Ocean. It's developed by a consortium, and it it's based on a state-of-the-art modeling framework for the ocean. This can be made a part of both weather forecasting models, and it is, and long-range climate models. So it does support research activities and forecasting services at the same time. The link down there gives the main page for NEMO. There are three components to NEMO. There are three main components to NEMO. The ocean part that models the thermodynamics and the dynamics of the ocean, how the water moves, how the salt moves, how the temperature varies. And it solves a large system of differential equations, of partial differential equations, so-called primitive equations. Then there's an NEMO ice, which models the sea ice, and both thermodynamics and dynamics, the salt that may be included in the sea ice, and variations in the thickness that may be smaller than the grid size. And then there's NEMO Top that models tracers, transport of tracers, and biogeochemical processes using a subcomponent called Pisces. And we're going to be using that for the HPC benchmark. NEMO comes with several reference configurations already included, and that provides very easy initial testing for new users, and also it can be used to validate new developments for those experienced users that are doing further development of the model. The instructions for configuring and using these reference configurations are found in the link that's right there. So for this competition, we have selected at the suggestion of one of our sponsoring academic sites is Gyre Pisces. It includes three components: the ocean one, the sea ice, and Pisces itself, and one easy-to-use feature is that it does not require additional input files, just some configuration files. So, what is it? Gyre Pisces is an idealized configuration of a system of double gyres, meaning regions of the ocean going around circulating in the northern hemisphere. Beta plane approximation, not being an ocean expert, I don't know what the beta plane approximation is. Well, I'll have to check it out. But it's based on a regular 1 degree horizontal resolution and using 31 vertical levels. This is a fairly small model. Newer model, or higher resolution models include 100, at least 100 vertical levels. It is coupled with the Pisces biogeochemical model. So to run Gaia Pisces as a benchmark, we only need to adjust 2 parameters. Of course, since this is pretty much a toy test case, the physical meaning of any results is limited. We are here interested not in what the results look like physically, but the absolute performance of the program on whatever you'll be running it on. So we are providing guidelines for building and running NEMO in this Gaia Pisces configuration. And these guidelines include instructions for building the required support libraries, namely HDF5, and HDF means hierarchical data format, NetCDF, which is a preferred format for weather and climate data exchange, and XIOS, which is an I/O support library for NEMO and other weather and climate applications. NEMO does use the message passing interface library, the de facto standard library for distributing the computational work and communicating among processes. So you will be needing some sort of MPI library. By the way, I'll go back to the previous bullet. The guidelines, we have tested this Gaia Pisces configuration using both commercial compilers and GNU, freely available GNU compilers. So you can test with either. So, and one last item that I really want to mention is that the domain decompositions in NEMO are not arbitrary. The program determines how to best distribute the work among the available processes, keeping in mind that not the whole planet is water. Okay, so not all values of the total number of MPI ranks result in a valid decomposition. For example, in one of the tests that we ran, we tried to use 60 nodes of a system having 40 cores per node, making 640 processes total. And NEMO in this configuration didn't like that. It could the closest number it could use was 623. If the total number of MPI ranks cannot be factored into what NEMO considers a valid decomposition, it will crash, but not before. Well, it will stop with an error, but it will provide a fairly long list of other possible decompositions that the program can be run on that are close to the number that failed. And that's pretty much what I had to show you. Thank you. If you have any questions, please go ahead and ask.